to this session of fluid machines, which will be a continuation of the earlier session. Earlier session we discussed about Francis turbine, a typical radial flow reaction turbine. This session we will be discuss just the reverse of that, that is a centrifugal pump where the fluid gains energy from the energy supplied mechanically to the fluid machines. Now, before going to the description of a centrifugal pump, how does it look like, what are the different components, what is its principle of operation, let us first understand the general pumping system and the general nomenclature related to the head developed by a pump. Now, for that I refer to this figure, just this figure. Let us see that the general pumping system. Now, if we refer to this figure, in general pumping we refer to lifting water, is a very general use if I tell, from a reservoir at the bottom to a reservoir at a altitude. So, if we take this way the general pumping system, which we mean actually pump helps a fluid to develop its energy for the transportation, for lifting from a lower level to a high altitude. So, if a general pumping system of this type if we refer to, then we will be able to understand the terminology associated with the head developed by a pump, head across pump and all these things. Let us consider this as a reservoir, this as a reservoir, it is seen clearly, it is clearly seen. This is a reservoir where the water goes through this pipe to the pump and it is delivered to a reservoir at high altitude. Let us have a reference datum here. I think you can see this diagram, from which I specify this level at this reservoir at height HA, from here to this level at this upper tank as HS, this is HS, this is HA, and Z1 is the elevation or the height from the reference datum to the inlet. This is the inlet to the pump, the section 1, and this is the outlet at 2, this is the delivery line Z2, and this is the pump. Now, in this diagram we see that here the liquid or the water at the free surface of this pump, this flows to this pipe, this there is a strainer to this, B is a point inside the pipe almost at the same level at A, then it goes to the pump at the inlet. You see that inlet, the fluid enters to the pump, and that inlet, the head which is there in the pump is comprises the pressure at P1 by rho g plus V1 square by 2g plus Z1. This is the head at inlet to the pump. Head at outlet to the pump, I am not writing everything, what is P2 by rho g plus V2 square by 2g plus Z2 is the head at total head at inlet to the pump. This is H inlet to the pump, this is H outlet, and the difference between these two, this pressure is measured by two pressure gauges. The difference between these two is the head developed by the fluid or the water through the pump. That means, head developed by the water in the pump, that is H outlet minus H inlet, that can be written as P2 by P1 by rho g for an incompressible fluid plus V2 square minus V1 square by 2g plus Z2 minus Z1. Usually, if the pipe cross sectional area are almost same for suction and delivery side, then we can neglect this, and if we neglect the elevation difference between the inlet and outlet, then the head developed by the fluid while flowing through the pump when it gets energy from the outside. This is the energy given from the outside. Then this is the head developed by the pump, that means head developed by the fluid in the pump. Now, if I want to know that what is the relationship between head developed by the pump with all these heights, then I have to write the Bernoulli's equation at some sections, that I am coming to. Now, if I write the Bernoulli's equation between the point A and a point at the inlet to the pump, then I can write at point A this pressure, if we consider 0, that is above atmosphere, then at A pressure is 0. Now, at A, if we write this, we have the velocity is 0. So, only this height HA. HA is the height from the reference datum to this level. Okay. That equals to, if we write it at C, at this point 1, rather I have given it at 1 here, then that is equal to the P1 by rho g plus V1 square by 2g plus Z1 plus the losses which take HF1, which takes place with all in the flow through this suction pipe or the inlet pipe, including the pipe bend. There may be strainer, all losses in the inlet pipe or the suction pipe. This is known as suction pipe, inlet pipe to the tank. Similar way, if I write the Bernoulli's equation between 2 and a point here, between this 2 point Bernoulli's equation, if we write, we have to take care of the energy input. But if you write the Bernoulli's equation between 2 and this point here at this surface, here F for example, so we get H A, that means this point HA plus HS is the potential head. Other things are 0, atmospheric pressure, velocity is 0. So, I am not writing this, straight away I am writing HA plus HS equals to what? No, sorry, we should write this way. We write this first, P2 by rho g plus V2 square by 2g, okay, plus Z2 equals to what? Equals to here 0 plus HS plus all the losses incurred in the delivery pipe, including the bends and all these things, HF2. Now, you see, if you make a difference between this minus this, as known as the H outlet minus H inlet, that is head developed, that means I want to, now you subtract this from this and substitute this as the head at inlet and substitute this at the head at outlet, and the difference between these two as the head developed by the pump, then you get a relation, that H is equal to that head developed is HS plus HF1 plus HF2. Now, this here one thing, this HF2, now HF1 represents all the frictional losses, HF2 represent a loss which is the frictional loss plus when it comes here in this tank, it comes with a velocity in the delivery pipe Vd for example. This velocity is lost, that is the exit loss, I told you Vd square by 2g. That means, if I write the Bernoulli's equation not at this point or at any point in the tank at rest, rather at this point at the exit end where the velocity is Vd square by 2g, here we could have written Vd square by 2g, then this loss could have been all the losses due to friction, but not the exit loss. So, this takes care of exit loss, that means this velocity head itself. In that case, the velocity head could have appeared here, you have understood. But when we take it here at this point this velocity is lost in the form of the loss of the kinetic energy at discharge. This is known as exit loss. Already it was discussed earlier. So, this is inclusive of the exit loss. That means mathematically if we subtract this from this, we get this expression, and this is H is equal to Hs plus Hf1 plus Hf2. Now, therefore, the head developed by the pump must be equal to Hs plus the losses, and this is obviously from common sense. You see that head has to be developed by the pump, so that liquid gets that head or the water gets that head to rise or to raise its height from this to this is Hs, and to overcome all the losses, that is Hf1 and Hf2 including the exit loss. That means to circulate or to force a flow to overcome the losses and to lift it to a height Hs from this level to this level, the developed head by the water has to be this plus losses, which can be found out by applying the Bernoulli's equation between this point and also between this point and this point. This is precisely the concept. Now, here also I will draw a figure which will be nice for you to see that if you follow the energy flow diagram here, if you head that this point is A, from A if you come to the point B, there is a little loss, that loss is due to the loss in the strainer. Then from B if you come to the point C or 1, whatever you call, this is the point B, this is the point A, there is a steady loss. This is the loss due to C or point 1, whatever you call C or point 1, this loss is due to frictional loss Hf1. Then at 1 to 2 C to D here we have abrupt rise D or 2 of the head, which is what? Energy, because of the energy input. Then from 2 if it goes this point, then this comes here. This is the loss due to friction, that is Hf2. If you do not take care of the exit velocity head, then this will still drop further to take care of the exit velocity head, that is Vd square by 2g. That means this point corresponds to this point or the point F here earlier defined, that means which is at rest. This is equal to your Ha plus Hs, this is Ha plus Hs. That means this is Ha plus Hs, that it represents only the potential head. That means if you draw the head line or the energy line, it is like this: A to B, B to C, C to D is abrupt increase because of the energy input, then again it is loss, again there is a drastic loss because of the exit loss. So, ultimately it comes here, which corresponds only to the potential energy, that means the elevation energy. So, this is the diagram, and you get an understanding that how the heads are represented. So, this is known as static lift in case of centrifugal pump. Static lift plus all the losses inclusive of velocity head. If you tell it is only the losses in the delivery pipe, frictional losses, then you have to add the velocity head. That means there in that case you are applying the Bernoulli's equation here. But if you take care of the fluid at rest in the upper reservoir, then this will be included in this. This is together as Hf2. This is the concept. Now, after this I will come to the description of a centrifugal pump. Now, a centrifugal pump consists of 3 different parts. Let us consider first. Here it is just the reverse of the reaction turbine. Here the fluid enters here. Now, here this is this rotating shaft. This is known as impeller eye. It is not shown here. Now, first of all I tell you that this consists of a rotating part. This is the shaft. This is the shaft. This is the shaft. Sorry, this is the disc, rotating disc. Sorry, this is the shaft. This is the rotating disc, and the blades or the vanes are of this type which is attached to the rotating blade, and this is the rotating part of the, this is rotated, actually this part is not rotated, this because of this, avoid the clumsiness, it is given, this part is rotated, this is the rotor of the pump. What is this part? This is shaft, this is a disc, and on this disc the vanes or blades are attached, there is a ring. So, therefore, this part, inner part is rotating part, which is the rotor of the impeller and is known as rotor of the pump and known as impeller. This is the rotor of the pump and known as impeller. Then surrounding the impeller there are some static vanes like the guide vanes and wicket gates of turbine. These are the static vanes, these are mounted on a ring after the impeller blades, and these are static, and this creates a diverging passage in the direction of the flow. Now, this inlet part is the impeller eye, this is known as impeller eye. I am coming and about the flow directions. Then surrounding this rotate is fixed the vanes, this acts as a diffuser, that is why these are known as stationary diffuser vanes. This is the stationary vanes, this is the vane rings, this is the vane rings, this is the stationary vane. Then it is surrounded by again a spiral casing where the flow direction is that which gives an increase in flow area in the direction of the flow, and this is known as volute casing. In some pumps which are of smaller capacity, there this is the impeller, this is the rotating blades or vanes, and this is the disc, this is the rotating vane or blades, this is the disc. There is no stationary diffuser vanes, okay. After this impeller there is only a volute casing. Now, I tell you the principle of action. Now, water is sucked at this eye of the impeller eye in an axial direction, that means it is a direction perpendicular to this plane. Then it is turned in a radial direction like this to flow through these passages of the impeller blades here, and this is a radially outward flow machine. Obviously, a pump has to be radially outward flow to gain its pressure, its inlet radius should be lower than the outlet radius. So, therefore, it is an radially outward flow, and while flowing through these rotating impeller blade passages, the section is diverging, that means its relative velocity is decreased and as a consequence pressure is increased. So, therefore, when it comes out from the impeller blades passages, it has increased kinetic energy because of the again impulse action of this impeller. It imparts kinetic energy of its moving part to the fluid gains kinetic energy, and at the same time the pressure is increased because it flows through a divergent stationary duct, and that is why it is known as stationary diffuser vane, because these passages created by the stationary blades or vanes acts as a diffuser. Here after the impeller it is the relative velocity increases and pressure increases. After the impeller what happens, I am sorry, just a little bit mixed up things, that through the impeller when it flows there is a increase in the pressure because of decrease in the relative velocity due to the diverging passage provided by the impeller vane. Now, while coming out of the impeller, the liquid or the water has both high kinetic energy, just I have told, because of the impulse action, that is the kinetic energy imparted by the rotating impeller blades to the liquid, and at the same time it has a higher pressure energy or higher static pressure because of this diffusion, that means increase in pressure because of its flow through a divergent duct. Now, when it comes out from the impeller, what we require? We require to convert the part of the kinetic energy in the form of pressure energy, because at the final outlet of the pump we require the water should come at a high pressure, but at a relatively low velocity, which will be required to maintain the flow, to deliver the water, but mostly it should be there in the form of static pressure. So, therefore, as we want the outlet at a high pressure but less velocity relatively, so we want to convert a large amount of kinetic energy which has been imparted by the rotor to the water to convert it into pressure. So, that is being done by the static vanes or stationary vanes, because it simply provides a divergent duct. That means this work, this is not there here, this works as a diffuser, that is why this is known as stationary diffuser vanes. Okay. So, therefore, in stationary diffuser vanes, part of the pressure energy, a part of the velocity energy or kinetic energy is converted into pressure energy or static pressure. The rest part is converted into again the pressure energy in the volute casing, since it flows in the direction of, in a way the direction of flow, the cross sectional area increases. For small capacity machine, what happens? We do not have the stationary vane, diffuser vanes, we only have a volute casing which is sufficient enough to convert the a major part of the kinetic energy at the outlet of the impeller to pressure energy. Finally, at the delivery end here, we have the water coming out with an energy received from the pump, different parts of the pump or components of the pump, in the form of more of static pressure or having more pressure energy and less velocity. Okay. This is the different components of a centrifugal pump and how does it work. So, at impeller the liquid or water is sucked almost in the axial direction. This is the impeller eye where the liquid water is sucked, and it is then immediately turned almost 90 degree in the radial direction, just the reverse of the Francis reaction turbine, while it flows through the divergent passage of the impeller blades, and also the impeller blade rotates, where it gains pressure while flowing to the divergent part and gains the kinetic energy because of the impulse action, and energy is being received or taken by the liquid or the water while flowing through the impeller. Then in the stator part, the fixed stationary vanes and the volute casing, what is done, a major part of the kinetic energy at the outlet of the impeller is being converted to pressure, static pressure. Okay, with this in the background, let us now go to a focus on a typical vane or blade in a centrifugal pump. A typical vane or blade in a centrifugal pump is this type. Here we show a impeller section, 3 blades. Here the rotation is in this direction and blades are such they are curved in the opposite direction. This is known as backward curved vane, and usually in centrifugal pump we use backward curved vane, which I will explain afterwards why. A typical backward curved vane which is just curved in this way, where the rotational motion is in the opposite direction. Okay. Now, for this type of typical vanes, impeller vanes, a velocity diagram is like this. We take a middle line here which is parallel to the, which is this curvature is same as this is the representation of the impeller vane. So, at the inlet the velocity diagram is like this, because at the inlet the fluid flows in such a way it has got a very low whirling component of velocity. This is the inlet velocity diagram, this is VR1, this is the absolute velocity V1. I draw it here, the impeller, this diagram is like this is like this. So, this is like this is V1, this is U1 and this is VR1, in such a way that if you make the component, this is VW1 which is very very small, almost 0. So, this angle is such that the tangential component of velocity at the inlet is almost 0, and this angle by the nomenclature is beta 1, that is the relative velocity angle. That means, sorry, this is VR1 this direction, relative velocity angle, that is the angle of the vane with the tangent at the inlet. So, this is U1 clearly written, this part is VW1 which is very less, and this is V1, this is beta 1, this is alpha 1. At the outlet you see, this is clearly shown that similarly the outlet, the relative velocity must match with this direction of the blade. So, this is omega is this, that means the U direction is this is the direction of the U2, this is U2, and this is your V2, this is your V2, again I am writing, this is VR2, it is written, this is U2. So, this component is VW2. Now, head developed by the pump given to the water is equal to what? VW2 U2 minus VW1 U1 by G. The nomenclature of the angle remains same, beta and alpha, 2 is the suffix for outlet, and this is the flow velocity at the outlet Vf2. Similarly, this is Vf1. Actually, Vf1 equals to V1 to reduce this Vw1. It is the similar reason by which Vw1, W1, the Vw2 at the Francis turbine outlet is 0, Vw1 is 0 because it can give maximum work, the rotor, to the water. So, here Vw1 is very less, is almost 0. So, H becomes equal to the head given to the water is VW2 U2 by G. Now, here we define an efficiency known as manometric efficiency. Why it is known as manometric efficiency? Now, it is usually defined as manometric efficiency. This is because I tell you that when we discussed about the head developed by the pump in terms of the measured pressure gauges, that pressure. Now, we see that this is the head developed by the pump, we measured the pressure at the inlet and outlet, at the inlet and outlet, and if the velocities at inlet and outlet is like this and the change in the elevation head. Now, if we neglect this thing, that means if we consider the velocity at inlet and outlet of the pump is almost same because of the same cross sectional area of the pipe. So, therefore, the velocity is coming with a low velocity, then ultimately it imparts energy, gains high velocity, it is being converted by the diffuser, vents and volute casing to pressure, and ultimately coming with the low velocity, and these velocity are almost same because ultimately by continuity equation, if the diameter of the pipe are almost same, they are same. Then therefore, these differences between static pressure and the elevation head is the piezometric pressure drop which can be registered by a manometer. Manometer registered a piezometric pressure drop. If we neglect this, then it will be simply the static pressure drop. So, that is the reason, there is nothing great, that why this head is known as manometric head. Sometimes you will see in the book it is written manometric. That means this head which is developed by the pump given to the fluid can be measured by a manometer. That is why it is known as manometric head. And now, this head if we represents at H, then the manometric efficiency is this head H developed, and this is the head, it is known as work head given by the pump. So, this is the head developed. So, now I write this head is the head developed by this one VW2 U2 by G. Now, this is the head work head, this is the head developed by the fluid. Try to understand, again I am writing, this is the work head given to the fluid by the rotor. This is sometimes known as the work head given to the rotor. So, everywhere I am writing H, you may be confused that this H is the head given by the rotor to the fluid, or rather you say the rotor head or the impeller head. Rather you say this head is you defined as the work head, H work. Work head given by the impeller to the fluid, out of which the head developed by the fluid is this one, which is measured by its pressure. If you neglect the velocity head, neglect the Z2, Z1, so it is measured by the pressure. So, therefore, this is the output, that is head developed. So, therefore, eta manometric will be this head developed divided by the work head. Work head means this is the head given to the fluid by the rotor. So, therefore, this is GH divided by VW to U2. Now, the question comes that what is the difference between these two? That means this is less than the head. This is from the principle of the angular momentum change. Okay, this is the energy given to the fluid in the machine, okay, while it flows through the impeller blade passages, and this is finally the head developed. Why it cannot get this head to be developed? Because of the different losses, viscous losses, other losses associated with some phenomena known as slip that I will describe. Because of the losses in the impeller, mainly the viscous losses, this and these are not same. This is the head developed measured by the pressure at the outlet and inlet, and this head developed is almost equal to the change in the pressure head P2 minus P1 by rho g. If we neglect the change in the kinetic head or the kinetic energy per unit weight at the inlet and outlet, and also the potential energies because of the change in the height or the elevation, then this is the output and this is the head given. VW2 U2 by G, numerator is H. So, ultimately this becomes this expression of the manometric efficiency. I think you have understood this clearly. Now, next to give it that velocity. Now, we will explain the slip, a phenomena like slip. Now, you will explain a phenomena like slip, which is very important. Now, earlier we have discussed the velocity triangle. Here, of course, the figure which I have taken, this gives just earlier the velocity was in opposite direction, here the velocity was given in this direction, does not matter. Accordingly, the impeller blades is like this, because impeller blades are always backward curved facing. You see, this is the direction of rotation, it curved in the opposite direction like this. Okay. Now, what is slip? You have to understand carefully. Now, slip is like this because of this curvature in the blade. When this is a rotation, there is a rotation and the fluid flows through this channel. Here is the concept, fluid mechanical concept. Then what happens in the, this is the leading edge and this is the trailing edge. So, the leading edge, this is the leading edge. So, because the motion is in this direction, so there is a rise in pressure in the leading edge and there is a fall in the pressure. There is an increase in pressure in the leading edge and fall in the pressure in the trailing edge. How? This is because of a typical curvature. This is because of this typical curvature which induces this thing. This is almost similar to that of flow through an aerofoil. This is because of this curvature, the fluid pressure here is increased and fluid pressure here is little bit decreased. Okay. So, therefore, there is an acceleration taking place of the fluid, that means the fluid velocity increases in this side and decreases in that side. So, this type of difference in pressure creates a circulation. You see, this circulation is shown like this, there is a circulation. So, this is actually in this figure, there is a circulation, this is a circulation. A circulation takes place which makes this distribution of velocity in the passage very much non-uniform. So, velocity in this passage is not exactly uniform, but the non-uniformity to a great degree is caused by this phenomena, and the velocity distribution becomes like that, and this phenomena is known as slip, because of which there is a circulation around a blade. In the leading phase there is an increase in pressure and trailing phase there is a decrease in pressure, and because of this there is a non-uniform distribution which ultimately results into a detrimental thing. What is that? Earlier we had a velocity triangle which is given by the dotted line, where the relative velocity here which makes an angle beta 2 which is equal to the blade angle or vane angle at the outlet because of shockless exit from the pump. Okay. But because of this non-uniformity of the velocity, ultimately the the relative velocity of the fluid at the discharge with respect to the impeller vane, the angle is changed, deviated, then the solid line shows this velocity triangle under the actual condition where the relative velocity Vr2 follows a angle beta 2 dash which is different from the vane angle, which is different from the vane angle. Okay. So, this causes apparently a change, that if you compare this two velocity triangle, this is the velocity triangle in the ideal condition, this graph is ideal, that dotted, where Vr1 Vr2, that is the velocity, relative velocity at the outlet, makes an angle beta 2 which is the angle at the impeller at the outlet, and whereas the actual case beta 2 dash is less than the beta 2, for which we get, if you compare this Vw2, that means the tangential component, sorry here you cannot see, at the outlet earlier was this much from here to here, this length, but now this actual case it is this much, this is this much, try to understand. Earlier it was how much? The Vw2 is this much, sorry, not this much, this much, this is the Vw2, this to this, and now this is this much Vw2 dash. So, therefore, Vw2 dash is less than Vw2. Because of this, as it shifts like this, beta 2 dash is less than beta 2. So, therefore, you see the tangential component of the absolute velocity which is responsible for the head developed is lower than the tangential component of the absolute velocity in the ideal case. And this difference delta Vw2, that is equal to Vw2 minus Vw2 dash, is known as slip. And a parameter is defined as the slip factor sigma s as the ratio of this Vw2 dash Vw2. Vw2 dash is less than Vw2. So, therefore, actual work done or actual head imparted by the rotor will be u Vw2 dash divided by g, which is sigma s into Vw2, I write first u2 by g. That means, the theoretical work done by the ideal case without slip will be multiplied by a slip factor to give this work done. So, because of this slip, sigma s is always less than 1 here, and this is the situation where sigma s becomes always less than 1. So, the work head imparted to the fluid is reduced. This is because only of slip. Here one very important concept should be known to you. This slip occurs not because of viscosity. So, this is irrespective of the viscosity. This is a phenomena which occurs because of the typical curvature of the blade and because of the flow along with the rotation. Okay. So, therefore, the rotation is given to the flow, at the same time the fluid flows in this direction, which causes a circulation because of the rise in pressure and fall in pressure in the leading and the trailing faces of the blade respectively. So, this is a typical fluid dynamical phenomena similar to that of flow of fluid past an aerofoil, where this phenomena occurs, there is an increase in decrease in velocity in the leading side and increase in velocity in the trailing side, and which makes in this type of flow in the passage a non-uniform velocity distribution. So, this is irrespective of the fluid viscosity. So, apart from that, there are viscous losses, skin friction losses and other viscous losses at the entry and exit in off design conditions when the relative velocity does not match the vane angles, but this is added with a slip loss because of this phenomena of slip. Now, after this, very important thing is that we will consider that the characteristic diagram of the head discharge characteristic, which is very important. Usually a pump is HQ characteristic. How to develop this for a pump? Pump is a pump characteristic curve consists a very important relationship between H and Q, head and the discharge. Now, if you see this diagram, then you can find out. Now, first of all, let me write the theoretical head, that is the work head, which is that I denoted as work head. The head, that means the work energy per unit weight given by the rotor to the liquid, is known as VW2 U2 by G. Now, let us do some small trigonometric thing. Now, VW2, as you see here, what is VW2? VW2, let us consider the ideal one. Let us consider the ideal one. VW2 is this one, which is this one. This is U2 minus this one, VF2 cot beta 2, because this is beta 2, that means this is beta 2. Okay. So, this is like this, that means if I draw this here, this is the ideal diagram. If I draw the velocity diagram here, okay, if I draw the velocity diagram here, if I draw the velocity diagram here, so then therefore we see that this is the V2, okay, this is the VR2 and this is the VW2. This I am taking from this figure where I have explained the slip, that means this is the U direction, U, U2, this is the U2, this is the U2, this is the U2, okay. That means this is the impeller and this is impeller blade and this is rotating, this is the typical impeller blade and this is rotating in this direction omega. So, okay. So, if I take this, then this is nothing but beta 2. Okay. So, this is written as U2 minus V, now this is VF2, this is VF2, U2 minus VF2 cot beta 2, VW2 into U2, this is into U2 divided by G. Okay. Now, U2 minus VF2 cot beta 2 U2 by G. Now, U2 is what? U2 is pi d2n. Now, if U2 is pi into, now this d2 I am representing as the d as the impeller diameter. This is one parameter d we define here. The diameter of the impeller means the outer diameter, pi d into n. So, U2 is pi dn. If you substitute U2 as pi dn and if you write this expression with VF2 as the flow rate, so therefore we can get an expression U2 square, that means H theoretical is equal to pi square d square n square minus U2 into VF2. So, VF2 is again we can write as flow rate divided by the cross sectional area, which is the area at the outlet, pi d into B. I am writing in terms of cross sectional area. If you do that, then you will get an expression pi d n by A cot beta 2, that means VF2 is this one q by A into U2. U2 is again pi dn, so pi dn has come q. That means I want to develop a relationship between theoretical discharge and the flow rate. Now, for a given pump impeller diameter and the rotational speed, this is constant and defined as K1. Similarly, for the different, for a given geometry, pi d n A cot beta 2 is constant, I define as K2, this. So, this will be by G obviously. So, here everything will be by G because we are writing the theoretical head. So, this divided by G. So, therefore, there will be a G, K1 and K2. So, H theoretical is K1 minus K2 Q. Now, we consider a typical this type of backward curved vane, rotational motion in this direction, curvature in this direction, so that beta 2 is acute and this cot beta 2 is positive and K2 is positive greater than 0. Then in that case we see that theoretical head is bearing a linear relationship with a negative slope with the Q. Well, now you see this is being, give a page, this is being now how this is being derived. Now here I draw the HQ characteristics, very interesting, H and Q. Now H is K1 minus Q, so let me express this expression. This is the theoretical head H theoretical, which is equal to K1 minus K2Q, as I have developed K1, K2 are the constants. Now from this I am going step by step the actual head discharge characteristics. From here I just deduct the portion responsible for slip, because due to slip H is modified at sigma s into H theory, which is what? H theory 1 minus sigma s into H theory, that means this can be written as H theory plus 1 minus sigma s into H theory, so that we can deduct this 1 minus sigma s part from here and can draw the curve, and moreover this slip depends upon the flow rate. More is the flow rate, more is the slip, and less is the slip factor. So therefore the slip loss is more when the flow rate is increased. So this portion, this is 1 minus sigma s into H theoretical. These are the different flow rate 1 minus sigma s into H theory. That means if I deduct this from each and every point in the abscissa corresponding to a flow rate, I get a nonlinear curve with negative slope like that from the theoretical curve. Now we have to subtract two losses. One is the skin friction losses, HF due to skin friction, simple frictions due to viscous losses. Now this loss is actually proportional to, we know, velocity square. I have seen that in turbulent flow it is proportional to velocity square. Here it is proportional to velocity square, means qualitatively we can express that it is proportional to Q square. So if we plot it, this frictional losses, when there is no flow there is no frictional loss. So this is like this, the frictional losses, like this. This follows this law. So let us define this curve as 1, this curve as 2, this curve as 3. So 3 is the frictional loss curve. Now another loss we will consider H shock loss, because of the shockless entry and shockless exit at off design condition, because only at design condition we expect that the velocity will at the inlet and outlet will glide along the blade, but it will not be so. It will not be so. There will be a direction change in the direction at the off design condition. This can be expressed as a constant K. Let this K1, then let this K2, Q minus QD whole square. Why in this form? Because when Q is equal to QD, the design flow rate, then H shock will be 0. So if we separately express shock losses, then it is to be expressed K2 constant into Q minus QD whole square. So if you plot this thing, QD is a constant value, that is a design flow rate, design for a particular pump. So this is expressed this way, that this is a high value here, and then it goes to 0 at the design flow rate. This is the design flow rate QD, this is Q, and again it increases. That means it increases in both the ways, that means when the flow rate is less and greater than the design flow rate. Now if these two, sum of the ordinates of these two, that means two losses 4, that means sum of the ordinates of the curve 3 and 4, is being deducted from curve 2, means we take care of these two losses from this head developed, which has been found out from the theoretical head in consideration of the slip loss. Then we get finally a curve of this type. This is the typical HQ characteristic of a pump. HQ characteristic of the pump. HQ characteristic of the pump. Okay. Next is that different blade angles. Now, I will tell you the influence of different blade angles in the HQ characteristics. So far we have considered only the that one, that K1 minus K2, that only only the backward curved vein. Now you see there are three types of this we have only considered, that a backward curved facing vein. That means this is the direction of rotation, the vein, impeller vein curved this way, that means in the opposite direction to the rotation. It is the forward curved vein, that means its curvature is in the direction of the rotation, curvature is in the opposite direction of the rotation. And this is a flat vein, this is known as radial vein. In all the cases, if you draw the velocity triangle, you see the velocity triangle in all these cases as such. These velocity triangles we have dealt with so far consideration of in considering a backward curved vein or backward facing veins, where curvature is in the opposite direction of rotation. But if you consider a forward curved veins, this beta 2 is obtuse, greater than 90 degree, and here it is 90 degree. So therefore, in your theoretical head discharge characteristic, this K2 was taken as greater than 0 when cot beta 2 is positive, so that this negative sign is there. But when in case of forward, therefore we can tell that in a forward facing curved vein, K2 is less than 0. In a radial vein, K2 is 0 because beta is 90 degree, cot 90 is 0. And here, which we already considered, K2 is greater than 0. So therefore, head discharge characteristic is linear with a negative slope is valid for the backward facing vein, because K1 is positive. But in a forward facing vein, that K1 is less than 0, that means a K2 is less than 0, that means this is positive. This is linear with increasing slope, and in case of radial veins, it is independent of the discharge. So this, the influence of the different types of blades, that is the forward facing, radial and backward facing vein. This is the radial vein, VR2 is radial. These are the velocity, this is the VR2 in this case, gliding, that is a matching with this angle. This is the VR2 which we have already dealt with. So you understand these three velocity triangles very well. Okay. Then K2 less than 0 in this case, K2 0 in this, K2 greater than 0. So therefore with this we can show that theoretical graph, just little before I started with in deriving the HQ characteristics for a backward facing vein, was linear with a negative slope, which is linear with a positive slope for forward facing vein, because here K2 is, as we defined there, K2 is less than 0. Here K2 is greater than 0, because the equation is that H is K1 minus K2Q. When K2 is 0 here for a radial vein, so this is constant. These are the theoretical lines. So then if we again plot the HQ characteristics with this as the theoretical curve for radial and forward facing vein, and go in the similar way as we did for a backward facing vein, we go on considering the losses, slip, frictional losses, these shock losses, then this will come like this. For your information, I tell you that this will be like this. This is for head discharge characteristic of backward facing vein, this is for a radial vein, and this is for a forward facing vein. But the difference is that if we find out the power versus discharge characteristics, where the hydraulic efficiency also becomes a function of Q, efficiency becomes a function of Q. If you draw the efficiency, hydraulic efficiency or the manometric efficiency as the function of Q, you will get a curve like this. So, if you take care of that and if you draw the power Q characteristics, you will see this will go like this. This is very important, that power Q characteristics for a backward facing vane is like that. This is for forward facing vane and this is for radial facing vane. So, one very important thing comes out in this context is that for a forward and radial facing vane, these are your concepts, that the power is a monotonically increasing function of the flow rate. So, therefore, what happens that for a backward facing vane, the power is not a monotonic function, power is giving a maximum here and then it decreases in both these sides. This gives an advantage to use a backward facing vane. Why I am explaining you that in a backward facing vane, it is found that the maximum efficiency occurs in the maximum power range. Okay. Now, if a machine does not operate on the design condition, if it operates on the off design or part load condition, not at the rated condition, then what happens? For example, the flow rate is increased, then what happens? The power is decreased. So, therefore, the motor is safely can be run, the motor is safe to be run at this condition. This is known as self-limiting characteristics. But what happens to a forward facing vane? Let us understand. Forward facing vane, you want to operate somewhere here which corresponds to the maximum efficiency. But by chance the flow rate is increased, it goes to a off design condition where power will be more. So, therefore, we have to specify the motor or we have to rate the motor for some higher power. You understand? So, what will happen? There will be two effects. If we rate the motor for higher power, taking a gap or a safety measure, factor of safety type, so that it can take care of the off design condition when the flow rate is increased, the power requirement. Then most of the time when it will be operating on the design condition, it will be underrated. That is a loss of energy. But loss of energy means that is a detrimental thing for the pump, that it is underrated. But more risky is that if we do not rate for a very high power pump, then if we rate a pump which will deliver a power corresponding to the design condition, by chance the flow rate increase, then it goes to the off design condition, the motor may fail because it will be running under a high power for which it is not rated. You understand? So, this is the drawback or the danger in using the forward and the radial vanes, whereas the backward cut vane has these advantages of self limiting characteristic. This is the reason for which we use a backward facing or backward cut vane in centrifugal pump. Now, next is very important thing is that net positive suction head of a pump. Now, you see in a pump the most vital point is the inlet to the pump, because here the pressure falls below, obviously because it is coming from the sump, that is this is known as sump, that the level here. Now, if we apply the Bernoulli's equation between these 2 points, we will see that this is the cavitation, that we will see that if we apply the Bernoulli's point between the inlet of the pump, let us consider the pump like this and let us consider simple schematic diagram where from pump is taking water. This is known as sump. Now, if we consider this as 1 and this as 2 inlet, and if I write this P2 by rho g, it is very simple, and if the pump is there at some height z from this level of the sump, then P2 by rho g plus V2 square by 2g, simple Bernoulli's equation, plus z plus, sorry, rather I should write this is the direction of the flow, this first. So, it will be better for you, P1 by rho g plus V1 square by 2g plus is equal to Z is 0 here, P2 by rho g plus V2 square by 2g plus the losses in this pipeline. Now P1 by plus the Z, yes, first is Z plus HF. Time is short, that is why I am in hurry. So this P1 by rho g is the atmospheric pressure, Pa by rho g. V1 square by 2g is 0 here. So therefore we can write P2 by rho g is Pa by rho g minus V2 square by 2g plus Z plus HF. Now you see, obviously the pressure here is suction pressure, similar to that in a turbine. Runner outlet the pressure is lower than the atmospheric, here pressure is lower because it is drawing water from the atmospheric pressure. So more is the elevation, more is the velocity of flow, more is the losses, more severe is the suction pressure, and obviously this P2 by rho g, or rather P2 has to be greater than PV to avoid the cavitation, that is vapor pressure at the working temperature. So therefore you have to be very careful in installing the pump, that if it is installed at a higher elevation Z and at the same time, so cavitation is likely to occur. So therefore it has to be, you have to be careful that pump should be installed close to the sump. Similarly the loss of head also should be low. So therefore this is the reason for which suction side diameter is usually made little higher, and we should eliminate all sorts of bends in the suction pipe which should not contribute to the loss, so that this has to be severe, that means the pressure falls much below the atmospheric pressure, closer to the vapor pressure. Similarly velocity of flow in the suction pipe has to be kept low, and this will be low if we make a higher diameter of the suction pipe. So this is the basic concept, that these parameters have to be checked carefully so that cavitation is not occurred, and that is the reason when we pump water from a well, we do not place the pump on the top, so that a big pipeline going to the well will start pumping the water. This will create cavitation. We have to check this height should no way be higher than the atmospheric pressure, height of water corresponding to the atmospheric pressure. Now based on this, similarly we define a net positive suction head, that is NPSH, a net positive suction head, that is NPSH for the pump as this. Here I will denote this as the inlet pressure to the pump, which is P2, as I explained the phenomena, plus Vi square, that means the pressure head plus velocity head at the inlet to the pump, that means it is basically the pressure head and velocity head at the point where the minimum pressure is reached. It was in case of turbine, outlet to the turbine, it was denoted by E, inlet to the draft tube, here it is inlet to the pump I minus the head corresponding to the PV by rho g, and this is actually can be written as NPSH, and this already I have shown you that this thing P2 by rho g plus V2 square by 2g, if we take this side, will be atmospheric pressure minus Z if we neglect the losses, or if you take the losses, it will be atmospheric pressure rho g plus Z minus losses P2 by rho g plus V2 square by 2g. That means the sum of pressure head and the velocity head at inlet to the pump. So therefore this will be P atmospheric by rho g plus P atmospheric by rho g plus Z minus Z, minus HF, and a parameter similarly minus PV by rho g, I am sorry, minus PV by rho g, and similarly a parameter Thomas cavitation parameter is defined as Thomas cavitation parameter is defined as P atmospheric, all this thing writing and this short time it is very difficult, PV by rho g divided by the total head H, And similarly, a critical cavitation parameter is defined as the inlet head, that means Pa by P atmospheric by rho g minus Pi by rho g. This is Z minus Hf. Similarly, I write here Pi. The similar way it was done in the, and a check is made between sigma and sigma c. Now, Pi by rho g has to be higher than Pv by rho g. So, therefore, sigma has to be greater than sigma c. So, again in the similar way we compare sigma and sigma c to decide the installation height of the pump and also the frictional losses, mainly the installation height of the pump. So, that sigma is always greater than sigma c. So, this after this I will tell you very interesting thing as the character operating point of a pump, operating, which is very important, operating point, operating point. What is operating point? Now, we have come to know that the HQ characteristics of the pump is like this. We know this HQ characteristics of the pump is like this. At the same time, we draw the efficiency characteristics, that means the efficiency is like this. This is efficiency line, this is the head Q characteristic. Now, efficiency is maximum, that means we will always want that pump should be operated at this point. This is the design or rated condition of the pump. So, this is the design flow rate. So, pump should operate at this point, must develop this head with this flow. By its characteristic curve, if this be the flow, this will be the head developed, and that condition the pump will run at its maximum efficiency. But pump will run at which point? The operating point means that what should be its flow rate and what should be its head depends upon the system also, system characteristics. You have to understand this thing, characteristics, system characteristic. What is system characteristics? Try to understand. There is a pump, I take water from this sump. Let us consider this way. I give the water to a tank like this, to a tank like this, and this is my static lift, this is my static lift Hs. Now, when the flow takes place through this pipeline, pump cannot operate alone, pump has to fix with this pipeline. So, this pipeline forms the system. When the flow takes place through the pipeline, there are losses in the pipeline. So, therefore, the head developed must be equal to the loss plus the lift. When the flow tends to 0, the head developed will be simply the static lift. That means, the minimum head which is required, energy which is required for the pump to lift the water, even at extremely small velocity, should correspond to this Hs lift, because it has to raise the water from this level at the sump to that level at the reservoir. So, therefore, this is known as static head. So, line also should follow the same characteristics, but when the flow will go through the pump, then what will happen? In the pipe there will be losses, and that loss Hf is proportional to the Q square. So, therefore, the pipe will follow a head discharge characteristics like that, Hs plus Kq square. That means, pipe will tell that you develop some head which I will consume through friction by my frictional law Kq square, and if you do not provide a flow rate, that is a limiting case when flow rate tends to 0, I will develop a head H is equal to Hs. Okay. That means, pump will develop that head, and pipe as it attached with the pump will correspond to that static lift. So, try to understand this thing. This is very conceptual, that the system characteristics follow this. The head which will be developed here will go to overcome the resistance through the pipe, and it must follow the pipe resistance law Kq square, where Q is tending to 0 at very small flow rate, this pump should develop a head which is equal to the static lift. So, therefore, a pipe resistance should follow this equation Hs plus Kq square. This is known as the system resistance. So, this I will show like this is like this. That means this equation Hs plus Kq square, and this is known as system resistance curve. This curve is known as system resistance curve. So, when a pump is attached with the pipeline for its operation, then the operating point will be judged by the intersection of these two, because the head delivered and the flow rate must match with the pipeline system also, because head delivered must overcome the frictional loss, and this frictional loss must follow the friction law. The frictional loss must follow the friction loss, that is the loss of friction is Kq square, and that must be equal to the head developed, as this thing was told in the pipe flow problem, that the developed head, that means the head causing the flow, is equal to the resistance Kq square plus the static lift. This is the static lift Hs. So, therefore, this is an equation A plus Bq square type of thing. So, this is actually the operating point. This is the which may not be the maximum efficiency point. So, operating point depends upon the intersection of the system resistance and the pump, because when it is in operation, the head and flow must satisfy the HQ characteristics, HQ characteristics of the pump, and also the friction law characteristics of the pipe, which is the pipe or system characteristics. This is the operating point. Okay. Next, I will tell you about the pumps are sometimes used in conjunction, in series and parallel, like the pipe. Let us consider pumps in series. Pumps in series. What is pumps in series? Very simple. Now, let us consider a pump in series like that. Let us have a pump like this, which takes water from a sump and this is the outer casing. This way the pump is represented. Its delivery line, this is pump 1, is now connected to the another pump, and finally it is discharged. So, here what happens, two pumps in series, that means the delivery line of one pump is connected to the inlet to the other pump and go, and the final delivery. There may be more number of pumps like that. So, this is in series. In this case what happens, as very simple, the flow rate remains same. It is a series problem, series pipe, but the total head developed is the head developed by this pump, head developed by this pump plus the head developed by this pump, H1 plus H2. Now, how to make the characteristic of these two pumps together? It is very simple, that if you make the head Q characteristics for pump 1, let us have this head Q characteristics, HQ characteristics. Okay. Let me draw this, somewhere it will be 0. So, this has got an implication, when the Q is 0, when the Q is 0, this is the frictional head, okay, that is different, no head is developed, but Q is 0, there is a head developed, that you have to understand, that in a centrifugal pump, when the flow rate is 0, that means the valve is closed. Because of the movement of the impeller, the liquid gains some energy. So, it is at the outlet of the impeller and is coming to the diffuser, when diffuser does not contribute to its conversion of pressure, but the total energy gain in the form of kinetic energy because of the rotation of the fluid and the pressure energy remains within this pump as the head developed. So, therefore, head will be there even if Q is 0. This is an important concept, we have already discussed this. Now, for pump 1, this is so. Now, if there is in series the pump 2, and if you consider the two pumps are identical, 1 and 2, then what happens, we can find out by each Q, if we add the same head, then we can develop the, this will come to this same point. That means, if this is the H1, this is the H2. In the two pump it will look same H2. that means H1 and H2 head developed are added. That means, if we have the individual HQ characteristics, summing up the heads at the corresponding Q, because Q will be same, we can, this is the single pump characteristics, this is the single pump characteristics, and this is the combined pump. In case of series, combined pump characteristics, combined pump characteristic, okay, in case of series. So, that is the combined pump. In that case, if you have the system resistance like this, this is your static lift HS, this is your system characteristic, system characteristic, system characteristic. Then this is the operating point here for the single pump, but this will be the operating point for the combined pump. So, combined pump operating point will be the intersection between the system characteristics and the combined pump characteristic. Clear? This is the case for pumps in series. Similarly, if there are pumps in parallel, what happens? That pumps in parallel means they are like this, two pumps in parallel. That means both pumps inlet line is connected to the sump, but their delivery line is my drawing is not that good, delivery line is attached, that means delivery line is joined. That means pump 1 and pump 2, they are drawing water from the sump, the inlets are both, the inlets of both are connected to the sump, and finally the delivery are connected to a common pipe and final delivery. So, here what is happening, that Q1 and Q2 coming from the two pump is added, and in this case the head developed by this pump is the difference of head here and head here and head here, and since the head in the sump, common sump is same, so head developed by these two pump will be same, okay, and the distribution of Q1 and Q2 depending upon the individual pump characteristics. So, therefore, if we draw this thing in HQ curve, it is same as the parallel pipes. So, what happens if this is the characteristics for the single pump, HQ characteristics for the single pump, then at each H, now here H is same but Q. So, at each H if I add Q1, very simple, and Q2, if they are same, these two will be same. Similarly, here this is Q1, this is Q2. If we add, we can make the characteristic curves for combined pump, combined pump. This is for single pump and this is for combined pump. Here also the system resistance is, if this is the system resistance, the operating point, system characteristic or system resistance, characteristic, I am telling everything, so you can write. So, this is the operating point. This is the operating point for the single pump. So, therefore, for a pumps in parallel, you can draw this thing by adding the discharge for a given head, and you can draw it, and accordingly you can find out the operating point where the system characteristics is being intersected by the pump. So, I think we will conclude here. Okay, we will conclude here. Time is not there, we cannot start anything. Now, we can go to axial flow pump, but however, now for less time we will, where is the cap? We will conclude here, and I have given you the basic principles of centrifugal pump. After 2-3 questions we will conclude. I will tell them something at the end, so that after 2-3 questions I will conclude. Okay, please.
RCID 1046.
Hello.
Please.
Hello.
Hello, please.
Hello.
Good afternoon, sir.
Good afternoon.
The impeller of a centrifugal pump
Yes.
has backward curved vanes.
Yes.
If the direction of rotation is reverse, hello?
Then
The
it will
direction of
be,
the rotation is reverse. What would be the effect of?
now if the direction of rotation is
Yes.
reversed, then a backward curved vane will act as a forward curved vane. But the vane angles have to be properly designed in that case. The pump will work, but the losses will be more and it will lose its what is called that self limiting characteristics. So these are very practical things. I think that
What
it,
would be the
hello, and efficiency will fall definitely. Okay, next. This should be conceptual fluid mechanical question.
Hello.
Hello.
Good afternoon, sir.
Yes.
Hello.
Hello. Good
afternoon,
afternoon.
sir.
Yes. Good afternoon.
Sir, my question is, why for the impulse turbine the pressure remains constant in the moving blade, but for the reaction turbine the pressure decreases?
Okay. Good questions. And reaction turbine and impulse turbine, the difference is that in impulse turbine pressure should remain constant. So this is made in a way that when the water comes to the rotor or the runner of the turbine, it is in the stator of the nozzle. For example, impulse turbine, the entire pressure is converted to kinetic energy and it is expanded, or it is being flown to the it is expanded in the stator up to the atmospheric pressure to have the maximum kinetic energy at the outlet. So when it strikes the blade, the pressure is atmospheric uniform, so there is no question of pressure change. While on the other hand, in a reaction turbine, when the fluid flows through the runner, the fluid totally fills the runner and it is completely in a casing, so that the pressure is always above the atmosphere and there is a opportunity of pressure change because of the converging passages across the runner blades. You have understood. So for impulse turbine, what happens, the pressure, for example in a Pelton wheel, what happens in the nozzle, the expansion of the liquid takes place. Expansion means the pressure at the inlet to the nozzle is fully utilized, so that the discharge pressure is atmospheric pressure. And in a Pelton wheel, the jet comes at the atmospheric pressure and it strikes the blades of the Pelton wheel one by one as it rotates. It is like this. I just tell you that if you are interested in a Pelton wheel, the wheel is like this. This is the blade. This is the blade. This is the vanes of the Pelton wheel like this. A diagram like this, I show you this diagram like this, and a nozzle, number of nozzles are there, usually 6 to 8 nozzles are there. They issues the jet, that means here from the penstock, because of the lack of time I could not teach you, penstock the water comes and at high pressure at inlet to the nozzle, this is the nozzle, and nozzle fully converts this pressure to kinetic energy, and here pressure is atmospheric pressure, and as it rotates this engages one by one the blades. Okay, this is wrong, this is this blade, this is wrong. So this is this blade. This blade looks like this. It is known as tangential flow. The jet comes here and flows like this. The jet comes here and flows like this. This is like this, little bit like this. The jet comes here and flows like this. The jet comes here and flows. This is known as tangential flow machine. So you see in each blade, if you see this view is like this. The jet comes here and flows. So entire flow along the blade is at atmospheric pressure. No question of pressure loss. Only when it goes out, this velocity is less than the velocity v1. By the impulse action it transferred by the change of the kinetic energy, that is v1 square minus v2 square by 2, it imparts energy and it rotates. This is the Pelton wheel thing. So therefore you see in a impulse turbine, the entire pressure is being utilized to issue a jet at atmospheric pressure. So, therefore, there is no question of any pressure change in the runner or the rotor.
Yes, yes, sir. Sir, then I shall ask another question, sir.
Please.
Why for the Pelton turbine, the blade is so designed that it is symmetrical? That means each part is symmetrical.
No, this is the design of the blade in case of this impulse turbine. To get the maximum efficiency of the blade is designed in a symmetric way like that. Okay, this is the practical thing, the way it is designed, and to make the, to have the maximum efficiency of the blade is designed in a symmetrical way and with this angle. This angle is nearly something like 165 degree or so. Okay.
Okay, sir.
One question more.
Good afternoon, sir.
Good afternoon.
Hello.
Good afternoon, please.
Sir, I have a question in previous classes. So, any other relations between boundary layer and friction coefficient, sir?
Boundary layer and friction coefficient is very much related. You see the friction coefficient for a flow over a plate, flow over a surface, external flow, the friction coefficient is defined in terms of shear stress divided by half rho v square, I told. The shear stress at the wall for an external flow is very much related with the boundary layer, because shear stress at the wall is determined by the velocity gradient at the wall. You understand, for a flat plate, mu del u del y at the wall, and the velocity gradient at the wall depends upon the boundary layer thickness. What is the order of velocity gradient? Order of velocity gradient is that if you have the velocity at the boundary layer interface, which is the free stream velocity or velocity in the potential flow region, it is u infinity, and the velocity at the surface is 0. If the surface is at rest, the velocity is 0, no slip condition. So, therefore, the order of the velocity gradient is u infinity minus 0, that is u infinity divided by delta. So, if boundary layer thickness is low, that boundary layer is thin, boundary layer thickness is less, that boundary layer is thin, then velocity gradient will be sharp and the shear stress will be more and skin friction coefficient will be more. And if boundary layer is thick, the velocity gradient will be lower and the shear stress will be lower and the skin friction will be lower. Skin friction is defined, it is the manifestation of the shear stress. Skin friction is one normalized expression of the shear stress at the wall. Skin friction coefficient is usually used usually by the engineers in practice, but actually it is the shear stress at the wall, tau w by half rho v square, and shear stress at the wall is very much related with the boundary layer thickness. Clear? Okay. Okay.
Sir, one more question, sir.
No, then
Sir,
I please one more.
One question. Sir, while you were teaching the pipe process, sir, you showed me the Modi chart.
Yes,
Sir,
yes, yes.
that is the epsilon value for PVC pipes and stoneware pipes were not shown there. It was for concrete and
Okay, I
the
do
data
not,
available for concrete, cast.
that is
How
a,
do we get that data? Sir?
that I cannot tell you in the, that I tell you that in the diagram probably it is not there, I do not know whether it was there or not, that you can take from any handbook. This is a practical information, there is nothing related with fluid mechanical concept that you can get from. Moody did not present that in that figure, but that in, you see, when you solve a practical problem or a practical pipe made of certain materials, if you search for epsilon, you can get the handbook from handbook, or you can ask the people in the industry who keeps this handbook. So, this is an information. Okay. Now, I tell you one thing at the end, that you may have enough questions, I understand, and because of short of time, this is the concluding lecture I tell you today. Because of the short of time, we could not cover many things, and at the same time we could not many things, we could not cover something, especially in fluid machines. I am telling, in fluid mechanics part we have covered the entire thing comprehensively, but in fluid machines, so my things that to be told are like this, that you please see my NPTEL lectures which will be uploaded within a couple of days, or you can read different books. And regarding the questions, not only in fluid machines but also in the different other sections of the fluid mechanics taught by we three, you upload the questions, we will try our best to upload the answers as much as possible. Because of the short of time, again I am telling, it was not possible for us to entertain each and every question. But at the end I like to tell you yourself read. Self reading is very important. I am telling you, self reading and self thinking is very important in learning a subject, which we are doing throughout our life. We are the students, we are the learner throughout our life. When we teach our students, because of our job as a teacher in any university or institute, we are the teacher. But at the same time, we have to learn the subject for our own satisfaction, for our own inquisitiveness of knowing things, and at the same time to teach much better to the student. For that, what you require is that you have to read, you yourself have to read, you yourself have to think, and have to interact with people around you in through discussion of the subject. I think we will do that, and we have taken our best effort to present the course before you. Thank you.